Throughout history, human civilization shares one common trait: the tendency to bond and form communities, excluding of course computer scientists. Whether for protection, trade, shared interests, or a sense of belonging, communities have always played a vital role in shaping human society. To understand these social networks, mathematical graphs have been proven to be an invaluable tool that allows us to find meaningful patterns and uncover the underlying communities. In such a graph, each person is represented as a node, with edges between the nodes signifying friendships or other interactions. In this episode, we will embark on a journey into the realm of graph theory to explore an extraordinary graph clustering algorithm that navigates through networks to uncover communities. Welcome to the captivating world of Louvain. Chapter 1. What is a graph partition? We want to analyze communities, hence we should talk about what a community is. One thing to mention upfront: communities, clusters, modules, bubbles, collectives, they all mean the same thing for us and fall within the realms of graph partitioning, a discipline in computer science. Let's start with a simple experiment I wouldn't recommend in real life. Commence with yourself and write down to what extent you like people in your surroundings. If you're neutral to the other person, you don't draw an edge. You kinda like them, draw an edge with weight 1. You really like the other one, increase the edge weight. Hate the other one, make the weight negative. In our simple model, we assume that this happens mutually. If you don't like the other person, this person also doesn't like you, to the same extent. That's why our edges here have no direction, they are undirected. With people being too much of a hassle to deal with, replace them with nodes, oftentimes also called vertices. With that, ask people in your surrounding to carry out the same experiment with people in their environment, so that you can draw even more nodes, link them with edges, and attach some weights to them. And voila, that's all we need for a graph. Now, what's a graph partition? Well, it's just splitting up the graph into a mutually exclusive set of nodes. For example, that's a graph partition, also referred to as clustering, with 3 communities. That's another one. Or take that one, that's also a valid partition, in this case consisting of just one big community. One important question arises. The heck, why should I even care? The beauty of having an abstract concept such as a graph allows us to encode all kind of things into it and then find good partitions, not just for friendships. YouTube probably uses some sort of community detection algorithm to recommend you videos in your sphere of interest so that you can keep procrastinating. During research, a good partition of a citation network, where edges denote one paper cited another one, can lead you quickly to scientific papers you're really looking for. Finding good partitions of a graph is also relevant in medicine. One paper from 2015 tried to identify cancer driver genes based on genomic data and protein-protein interactions. Among others, it also used the exact same algorithm that we're working towards in this video. And that should be a strong motivator. If you're really not convinced, the beauty of math alone should suffice as a driving force. Speaking of math, let's formalize our graph partitions. For the moment, we ignore the edge weights and instead focus on the nodes, which we label from 0 to 9. This graph clustering can be written as a set of sets. The first set specifies which nodes live in the first community. Here nodes 0, 1 and 2. Likewise, we can do so for the remaining sets. For a different graph partition, we get different sets for our clustering. Maybe you agree that the second clustering here is a bit weird. Our goal will be to find the optimal clustering, whatever that means. We will discuss this notion in the next chapter. In order to find the best clustering, it might be worth to figure out how many possible partitions there are in the first place, so we know how big our search space is. Maybe there's just a few partitions. We start with a graph of 4 nodes. Pause the video and try to come up with all possible partitions for this graph. Note that this does not depend on the edges. That's why we don't draw them in here. 4 nodes and we get 15 possible partitions that we color code so that nodes with the same color belong to the same community. What about a graph with 5 nodes? We already get 52 possible partitions. put just one more node in it, and we end up with 203 petitions. Doesn't really sound linear, and in fact it's not. It's an exponential rise described by the so-called Bell number. With 50 nodes, there are already more than 1 billion possible partitions of our graph. Yes, 1 billion, and that's just 15 nodes. In real-life applications, we want to analyze graphs with tens of thousands or even millions of nodes. Unfortunately, this means that brute forcing is not an option, and we need a more sophisticated algorithm. Welcome, Louvain. But take it easy, this is our problem-solving agenda. We've already managed to encode a real-world problem, namely that of friendships and social interactions, into a mathematical concept, that is our graphs and the communities for the respective graph partitions. But we haven't found a metric yet that tells us how good a given graph partition is. And this is where modularity comes in, allowing us to turn this into an optimization problem that we will tackle in the last chapter, where the Louvain algorithm will try to find an optimum that is maximize modularity so that hopefully we will get a good graph partition. Let's take it one step at a time. Chapter 2, what is a good graph partition? Going back to our graph where we consider two different clusterings, what is it really that makes you favor the left graph partition over the right one? And how can we formalize this? Let's take a closer look at the left one. We notice that a lot of edges are contained within communities, compared to edges that run between communities. So why not use the fraction of all edges that run within communities as a metric to maximize? To write it down mathematically, we need to have access to the edges. For this, let's only consider the left part of our graph. Oftentimes, edges are encoded in an adjacency matrix, which has the weights of edges as entries. Here the part of the graph we consider has 3 nodes, so we deal with a 3x3 matrix. As an assistance to fill the entries, write down the node labels on the rows and columns, where the rows denote the starting point of the edge and the columns signify where the edge ends. For example, there's no self-loop connecting node 0 to itself, likewise for the other nodes, that's why we have zeros on the diagonal. For the other entries of the first row, consider node 0 and which edges it has to other nodes. There's an edge to node 1 with weight 1 and an edge to node 2 with weight 3. Similarly, we fill out the other entries. As a result, we find this matrix. Back to the whole graph, pause this video and find a 10x10 adjacency matrix. Here we go, there it is. Note how the matrix is symmetric with respect to its diagonal. For example, you can find pi twice in there, mirrored along its diagonal since the graph is undirected. With this encoding in mind, remember we noticed that many edges should lie within communities compared to between communities. But how to characterize edges within a community? Consider this edge which is within a community. Why? Because nodes 1 and 2 are in the same community, whereas this edge runs between communities, since nodes 2 and 3 are not in the same community. Finally, we can write down our first formula. We want the fraction of edges within communities. So let's first calculate the number of edges within communities, and weight it as we deal with weighted edges. We sum over all communities of our clustering, which in this example is made up of 3 communities. And then for every community, sum up the respective entries of our adjacency matrix A. Let's take a closer look at what this really means and split out the parts of this sum. For the upper left community, the term inside the parentheses evaluates to this expression. Looks familiar? Well, that's just the sum over every entry of the adjacency matrix of the subgraph. But wait, this means we actually summed up the edges twice, so we have to add an additional factor of 1/2 over here. For the very small community of just 2 nodes, we get this expression, and so on for the last community. Splendid! This is the formula for the weighted number of edges within communities. From here we don't have to go far to get to the fraction of all edges within communities. Simply divide by the total number of edges in the graph, which we get by summing up all entries of our adjacency matrix. Note how this sum also includes edges that run between communities. For example, the entry A23 only occurs in the sum in the denominator. Put simply, the fraction here is the number of edges within communities divided by the total number of all edges in the graph. Et voilà, our formula. Additionally, to make our lives a bit easier, we introduce m to abbreviate the denominator. Then rearrange to make it look prettier, and here we go, congratulations, our formula. This is the metric that we try to maximize with regards to the graph partition C, turning community detection into an optimization problem. So for very small graphs, we can actually make sense of the brute force approach now. Try out every possible clustering, plug it in our formula, note the result. And whatever clustering gives us the highest value, take that as the best graph partition. However, the sad truth is, if you do this for our sample graph, what you'll end up with is not this beautiful graph partition, but sadly enough, this one. Every node is in the same community. And you will find this outcome not just for our sample graph, but literally for any graph. Why? Take a look again at our metric. What happens when every node gets assigned the same community? This sum is basically useless then, as there's just one community, so we can just as well get rid of it and sum over all vertices of the graph. But then per definition of m, what we have is 2m over 2m, which is 1 or 100%. So obviously for this graph partition there are no edges between communities, as there is just this one community. And therefore this fraction is 1, which is the maximum value we can ever achieve. That's why we will always end up with this graph partition, which does not help us at all in understanding the communities of a network. But we can actually make it work. So far we just counted edges or their respective edge weights and aimed for a high fraction of edges within communities. But apparently that's not enough to constitute a reasonable metric. Here's a quote by Newman, who, together with Given, originally introduced modularity to the research community, pun intended. A good division of a network into communities is not merely one in which there are few edges between communities. It is one in which there are fewer than expected edges between communities. Emphasis on fewer than expected edges, not just fewer. He goes on, if the number of edges between two groups is only what one would expect on the basis of random chance, then few thoughtful observers would claim this constitutes evidence of meaningful community structure. On the other hand, if the number of edges between groups is significantly less than we expect by chance, or equivalently, if the number within groups is significantly more, then it is reasonable to conclude that something interesting is going on. I couldn't have stated it more clearly. So the main point here is that we should compare to a random baseline. But do we have to throw away our previous metric we made in sweaty handwork? Luckily, no. We want to compare to a random baseline. So we still need to know the actual fraction of edges within communities and compare that to the expected fraction. The new metric is called modularity, defined as the fraction of edges that fall within the given communities minus the fraction of edges that fall within the given communities if edges were distributed at random. So we compare the actual numbers we observe with a random baseline. And why do we subtract? Simple reason, given this definition, what happens when we consider a graph partition where the edge distribution is not distinguishable from random? Then the left term is equal to the term on the right, and we end up with 0 for modularity. So that makes sense as a measure. It evaluates to 0 if our graph partition is so bad we cannot distinguish it from random, and goes up to 1 when there are many more edges than expected inside our communities compared to edges between communities. Also note what happens when every node is in the same community. That was what we got when maximizing just the left term. But now, with such an assignment, the right term really punishes us. If there's just this one community, then, yeah, well, we expect 100% of edges to lie within it. That's the random baseline. But then that's also the fact, all edges are actually within this community. So both terms would evaluate to 1 and we end up with 0 again, which is good in this case since we don't want this weird community assignment to be the best choice. One thing to mention, this formula is not God-given. It just turns out that it makes sense and it has proven to be very useful for applications. So this whole derivation is not a rigorous proof at all, but rather a heuristic that we try to motivate. Right now, this formula is only written in text form. We need an actual expression to evaluate it. The left part is already completed with our initial metric, so on to the right one. What do we mean exactly by if edges were distributed at random? We can't just compare to any arbitrary random graph. To allow for a fair comparison between our actual graph and a random graph, let's stipulate some properties that should be preserved. Our random graph should have the same number of nodes n as our original graph, and it should have the same number of edges m. This makes sense, as otherwise what comparison would that be between a graph with 10 nodes and a graph with 1000 nodes and many more edges? We want to provide statements about our original graph and what kind of edge distribution we expect in it. Therefore, we should also compare to a random graph of the same size with respect to the number of nodes and edges. But then there's one more thing to preserve, and that is the node degree kv for all nodes, or also called vertices, of the graph. For example, if we assume every edge to have weight 1, then node 8 has degree 3, since there are 3 edges starting at this node. If in a graph where edges are distributed randomly, this node suddenly had a higher edge degree than in the actual graph, this would bias the comparison. That's why in the new graph this node should also just have 3 edges with an end in it. Or if we bring in edge weights other than 1, the degree of node 8 raises, for example to 13.7. So in the random model, node 8 could have more than 3 edges attached to it, but their weights have to sum up to 13.7 in this case. But for the sake of clarity, let's assume edge weights to be 1 for now. That is, node 8 has degree 6 in the random graph, which we need to fix so that it has degree 3 as in the original graph. Likewise, for the other nodes of the graph, they should all have the same degree as in the actual graph. For example, this one acknowledges all properties we wanted to preserve. At least it seems so. One error has slipped in. Can you find and fix it? Okay, so we have specified what randomness means in this term on the right. But what about its calculation? How do we get the fraction of edges that fall within the given communities if edges were distributed at random? Well, here's the fascinating idea behind it, making use of the so-called configuration model. It allows us to build up a network with a predefined degree sequence. That is to say, all nodes should have the same degree in the random network than in our original one, which is exactly what we want. It works like this. Take our graph and get your scissors ready. Cut the edges into 2 halves, leaving only edge stubs on the nodes, also called half edges. Since we had m edges in our original graph, we end up with 2 m edge stubs. Choose 2 stubs uniformly at random and connect them by an undirected edge. Continue with other stub pairs until there are no stubs left. What you end up with is a graph that preserves all the properties we were talking about: number of nodes, number of edges, and the node degrees. I think this is a beautiful model that we can leverage now. What is the expected number of edges between any nodes u and v in the same community? If we knew this expected value, we could easily get the fraction of edges within communities, just as we've done before, by summing over all edges within communities, doing this for every community, and dividing by the total number of edges. That's exactly what we need for our modularity formula. So then, what is the expected number of edges between 2 vertices u and v? For that, let's pick 2 edge stubs and ask ourselves, what is the probability that these specific stubs will connect? Starting with this one stub, what other stubs could it possibly connect to? It could connect to any other stub in the rest of the graph, or this stub, or this one, even to another stub on the same node, producing a self loop. but not to the same stub. The rule is just one end of an edge per stub. Okay, so the probability that this stub connects to this other stub is one outcome for the desired setting divided by 2m minus 1 equally likely other possible outcomes. 2m, as we have 2m edge stubs in the graph, and minus 1 since we cannot connect to the edge stub itself. With this, what is the expected number of edges between the two nodes? Node U has ku edge stubs and node V has kv edge stubs. So without being too rigorous, one could argue there's ku times kv pairs of stubs that possibly connect node U and node V together, so that the expected value becomes ku kv, possible outcomes, times the probability for one such event, which we calculated to 1 divided by 2m minus 1. If you're not satisfied with this, here's a more rigorous justification, introducing a random variable, encoding whether two edge stubs are connected or not. Pause the video if you want to read through it, otherwise we will now put together our final modularity formula, and this time really the final formula. Plug in the expected value that was still missing here to get the fraction of edges within communities if edges were distributed at random. Woohoo! Going back to our definition of modularity, we see that we also managed to formalize the term on the right hand side. And remember our first metric that didn't quite work out? That's the term on the left hand side. Putting everything together after the hard work, we arrive at this beautiful formula. Make it even prettier by consolidating, for example the sums and the factor 1 over 2m appear in both terms. So we have this term where Q stands for quality. When dealing with big networks we have many edges, so 2m is way bigger than 1, therefore the minus 1 is often dropped for the sake of simplicity. And that's the formula that gives you superpowers that you will find in literature. But sometimes you will also encounter an alternative formulation that might be easier to handle. Don't worry, in just 2 steps we're there. Step 1, use this identity for the right part so that we don't have to sum over different vertex degrees. Step 2, introduce 2 new definitions, twice the sum of the weights of edges inside community C, that is, edges with both ends in the community. Reminiscent of the sums, we use the uppercase Greek sigma letter as variable name. And we denote the sum of the weights of edges incident to nodes in C with sigma C hat. Note that incident is just a fancy way to say edges attached to a node. In other words, to calculate sigma C hat, we sum up the weighted node degree for every node in community C. Drop these definitions into the respective places and voila, we have a shorter and more manageable formula for modularity. So this is it. We've managed to formalize the concept of communities into a metric that is dependent on the graph partition we pass into it. Okay, that was quite a trip, wasn't it? But don't worry if you're not 100% sure about every detail of this formula that I've written down here again. We will now walk through an example to get a feeling for the calculation behind modularity. And in our case we have this graph. It has 4 nodes, it has some self-loops over here, all edges are undirected, and of course it's weighted. So for example, this self-loop has edge weight 14, this edge has weight 4. Now let's first look at the adjacency matrix, as we will need it for our calculation. What will the adjacency matrix look like? Pause for a moment and then we compare. So here it is. That's our adjacency matrix for this graph. Now we want to find out modularity for a particular community assignment. So for the start, let's take this one. Every node just sits in its own community. So our clustering of the graph is just given by this set of sets. Next we need to calculate m, as we have a factor of 1 over 2m in our formula. So what is m? Remember, it's there to roughly reflect the number of edges, but weighted as we deal with a weighted graph. So our formula is given by this expression. So we have a factor of 1/2 over here. And then we have 2 sums, u over u and v. And these sums, they go over all vertices of our graph. So we have to consider, for example, a0, 0, a0, 1, A1, 0, and so on. So basically that's just every entry in our adjacency matrix. We could just sum it up, but I think we can do better. Let's exploit the symmetry of this matrix. Aij is the same as Aj for every I and j. For example, we have 3, 4, 4, 1, 1, and only on the diagonal they're the self loops. Therefore, we can just multiply by 2 the entries above the diagonal. So 2 times 10 plus, and now we need the entries on the diagonal, 36. So that's now our number of edges, m, or as we need 2m, that's 56. Okay, awesome. So now we have our 2m, and then on to the main part, which is this sum over all communities. So we have 4 communities here. Let's start with the upper left one. It just encompasses this node. So basically sigma c that you can see above there, that's the sum over all vertices in our cluster. But as we only have this one node, we only get the entry A0, 0 in there. And what is A0, 0? That's just a self loop. So that's 14 here. And now we have to subtract this part. What is sigma c hat? Again, we only have one node in our community. So it's just the degree, the weighted degree of this node, which is 14 plus 4 plus 1 plus 1. That's 20. So we write down 20 squared. And now you can do the other parts, and we will compare in a minute. Good job. Our final result is written down here, 0.3463. That's our modularity that we've calculated by hand. Okay, now come on, one more example, and I promise it will be shorter now as we just consider the same graph, but with a slightly different community assignment, to get really a feel for how it works. So in our new clustering, we have 2 communities, one with nodes 0 and 3, and one with nodes 1 and 2. So C has changed now, I call it C2. The graph stays the same itself. So we still have the same adjacency matrix, and we also have the same value for m or 2m. But what has changed is these sigma values. So sigma c and sigma c hat, they are different now. First, consider sigma c. For this community now, we have 2 nodes instead of 1 node beforehand. If we consider the formula up there, we have A0, 0 now, plus A0, 3, plus A3, 0, plus A3, 3. That's just the sigma c that we have here in our formula. But as we can see, the same argument as beforehand applies. These 2 terms are just the same. 0, 3 is 4 and 3, 0 is 4, as we have an undirected edge here. So this term here will be twice the weighted number of edges that with both ends inside our community. So that's only this edge here. That's 8. And then we get A0, 0, that's 14, and here we have 4. They are only counted once. So as a sum, we get 26 over here. And then subtract sigma c hat, and sigma c hat is the weighted degree of all nodes inside our first community now. That is, for node 0, we have 14 plus 4 plus 1. For this node, we get 4 plus 4 plus 1, so that's 29 squared. Now again, it's your turn. Do the next terms, and then we will compare. There was only one more term to calculate, and then we get this number. So as you can see, compared to our first quality that we calculated, that has slightly increased now. So indeed, this is a better community assignment than what we had before. Now, what I find really beautiful about this example is that we can see the inherent trade-off that we talked about earlier when we derived the formula. This trade-off meant when we want to maximize Q, we have to maximize this term, minimize this term, so that the difference is really big. Maximization of the first term means many edges inside communities. Minimization of the second term means small total vertex degree in each community. So the second term favors lots of small communities, whereas the first term wants really big communities where lots of edges are in there. And now when we go back to our formula, we also see this in the calculation. So for example, if you take 20 squared plus 20 squared plus 7 squared plus 9 squared, that's 930. Compare that to 29 squared plus 27 squared, that's 1570. So that's a lot bigger here. And that makes sense because now we have more nodes inside our communities. Beforehand, every node was in its own community. Now there are more nodes, so the vertex degree got bigger. But then we also have to consider the first term. And when we do that, let's calculate 14 plus 16 plus 2 plus 4. That's 36. And then compare that to 26 plus 24, which is 50. So that's a lot higher here, and that also makes sense as we have more edges now inside our communities. Beforehand we just had the self loops, now we also have these edges here, which are totally inside our communities. So that's just one example of how you can calculate modularity by hand. You can now come up with your own graphs or just do another community assignment here. For example, what happens to modularity if we put all nodes into this one big community? What will we get for modularity then? Write it down in the comments below. And now you can also do your own graphs and tinker a bit with them. Maybe write your own program so that you don't have to do this by hand, because that's really tedious for big graphs. That's why we also just consider this very small graph. We are now in a position to approach the, in my opinion, most fun part. Chapter 3, Louvain, how to optimize modularity. This is our current state of affairs. In the last chapter, we've derived the modularity formula, which allowed us to rank different graph partitions according to how good they detect the underlying communities in the network. Having available this metric means we've successfully turned the problem of community detection into a mathematical optimization problem. Find the graph partition C such that the modularity Q of C is maximized. If you like to, you can think of this in 3D space, where you have different graph partitions lunging around in the XY plane, and for each of them, plot the respective modularity values on the Z-axis. Our goal is to find the global optimum, in our case the maximum modularity, so we don't want to follow these marbles into the minima, but rather reverse their action and get to the top of the mountains. Clear the stage for Louvain. Why this name? In 2008, Blondel, Guillaume, Lombiot and Lefebvre published a paper called Fast Unfolding of Communities in Large Networks. And the algorithm presented there became popular under the name Louvain, or should I rather say Louvain, a city in Belgium not far from Brussels. And Louvain-la-Neuve, word by word New Lion, is home to a university where Vincent Blondel was head of Department of Applied Mathematics around that time. He's now rector of the university. Let's have a first look at the paper. Oh, what's that? Our modularity formula in the introduction. Cool, we know that. What else do we have? On page 5, a nice looking graph that explains how the algorithm operates. Do you get a feeling of déjà vu? Well, you're right. For this graph, we've even calculated modularity in the previous chapter. I think we're now more than ready to finally tackle the inner workings of the Louvain algorithm. Let's consider a slightly simpler example to see how it works. Before we start, take your time to think of a graph partition you expect as outcome of the algorithm. Initially, Louvain starts with this graph partition. Every node sits in its own community, which we refer to as singleton communities. The first step is then nicely summarized by Closet, Newman and Moore, who developed another community detection method in 2004 that the Louvain algorithm draws on. Starting with each vertex being the sole member of a community of one, we repeatedly join together the two communities whose amalgamation produces the largest increase in Q. In the Louvain method, a similar procedure is realized by iterating over all nodes in a random order. For each node, for example node 6, we remove it from its current community and insert it into a community of one of its neighbors so that the modularity gain delta Q is maximized, where delta Q is just Q after our change minus Q before our change. For example, we find that inserting node 6 into the community of node 7 produces the biggest increase in modularity. This is also why Louvain is a greedy algorithm, as we always try to make the locally optimal choice. Keep going on and do the same procedure as every year for the other nodes. Note what happens to node 0. If we were to move it to the community of node 4, we find this doesn't improve modularity or even worsens it. That's why node 0 just stays in its community, as it is already the best one. Another interesting case is node 7, which will definitely stay in its community, as there are no neighbors located in other communities that 7 is not yet part of. We keep going until we've visited every node of the graph. And then do the whole thing again. We iterate over all nodes over and over until we reach a point where every node stays in the same community, as we have reached a local maximum of modularity. In our example, this is already the case for the next iteration. Visit node 6, it stays in the same community. Likewise for all other nodes. No improvement is possible anymore. That's when we know we've completed the first phase of Louvain and achieved a local maximum of modularity. Moving to phase B, community aggregation, which is quite fun and the name says it all. We construct a new graph where vertices are the communities of the first phase. That is, we encapsulate all vertices of one community into one new supervertex. Let's see how it works in detail. Edges within communities are condensed to self-loops with a weight of twice the sum of the edge weights beforehand. Why twice? Look at our modularity formula again, especially the definition of sigma c. Edges inside the community are counted twice, as we have already seen during the sample calculation. In the new graph, these edges are represented by a self-loop, which is only counted once since it's on the diagonal of the adjacency matrix. That's why we multiply by 2 here, so that modularity is the same in the new graph. The current phase is just for community aggregation. Modularity only changes in phase A. Do the same thing with the other 2 communities and we end up with this graph. But what about edges between communities? They also get merged together. For example, these 2 are transformed to an edge with weight equal to the sum of the weights of the edges beforehand. We had 2 edges with weight 1 respectively, now we have just 1 edge with weight 2. For the other edge there is just this 1 between the communities, so we simply take the weight it had beforehand, which is 1. So this is how our new graph looks like. As you can see in phase B, we have greatly reduced the complexity. Do you know why Louvain is also called a hierarchical clustering algorithm? This phase B is the reason for it. We've started with our initial partition with singleton communities. Q is around negative 0.118, so even worse than in the respective random graph. Then we optimized modularity until we've reached a local maximum and finally aggregated the communities so that we have this graph here after the first pass. We now calculate modularity for this new graph. However, notice that this is by construction also the modularity of our original graph with these communities. You will find Q is now about 0.372. It has increased, yay! And you might have guessed it, now we do a second pass, but with the new graph. Start with singleton communities, optimize modularity, and aggregate communities. The nodes on the right hand side apparently got merged together. If you're interested in the community of a node, for example of node 3, you start from the bottom and work your way up to the level you're interested in. After the second pass, you try to start with the third one and attempt to optimize modularity. However, you will observe that not even the first random iteration over the nodes in phase A yields any improvement. And that means the Louvain algorithm terminates. And we have found a modularity maximum. How does the respective graph partition look like? Here it is. We've already seen it. Would you have guessed this graph partition in the beginning? This partition achieves a local maximum of modularity. Due to the greedy nature of the algorithm, we cannot be certain that this is also a global maximum. But oftentimes for really big graphs, we're glad that we can even find a local optimum. Speaking of big graphs, fasten your seatbelts for the final coup. Louvain in action on a real-world dataset. Thank you so much for having joined me on this trip through the world of modularity and Louvain. I had a blast making this video, even though it was quite stressful at the end to meet 3 Blue 1 Brown's deadline. As always, everything takes longer than expected. A huge shout out to my friends who lent me their camera or microphone, helped fixing mistakes and improving the script. You really were a big help for me. Despite this video's length, there's so much more to discover. For example, papers I've linked in the video description, a website I've set up with even more examples, and a GitHub repo with my Louvain implementation written in Rust. That's it. Louvain has terminated for our graph, and I think it looks gorgeous. See you next time. Bye.